Hello, everyone. Today we're going to talk about marker-based versus markerless motion capturing systems. So as we all know, accurate motion capture is vital for biomechanics, whether it's for sports, rehabilitation, or clinical trials. And marker-based systems are currently the gold standard, but these systems can be very time extensive and can be prone to marker placement error. The motivation for me to do this project is during our labs, we had a lot of marker placement errors that corrupted our data, and I had experience working at the Human Mobility Lab with markerless systems before, and it was very minimal experience, but I know that markerless systems have a lot of potential to solve this issue because they're easier to set up, have broader applications because they're around half the setup time. They're more comfortable because you don't need to wear tight clothing. You can or worry about reflective markers, and you can use them in various environments for different diversity of groups of people because all markerless systems do is they use deep learning to place virtual markers on a person, and then they use AI pipeline to gather your joint kinematic data. So studies that have been done before show that markerless systems can have minimal variabilities of around 2.5 degrees compared to marker-based systems, but this is highly debated in a lot of literature that I reviewed, and my goal is to really evaluate how good markerless systems are and come up with some sort of a guidebook for labs or anyone to use to know when to use markerless systems and when to use marker-based. So my overall research question is, are markerless systems truly on par or superior to marker-based systems for biomechanical analysis? And my first hypothesis is marker-based systems are going to be better in dynamic movements, very fast movements. And my second hypothesis is markerless systems are going to be equally effective when you look at a specific part of the body, whether that's knee angle or elbow angle, etc. So the first hypothesis, marker-based systems are superior in dynamic movements. I think they're going to have a very low error margin in high-speed tasks compared to markerless systems. So marker-based systems are going to be much better at calculating your joint angles when you do activities such as jumping or running, etc. And my second hypothesis is when it comes to full skeletal models where there's hundreds of markers on an individual, marker-based systems are going to be superior because you don't have to place virtual markers on the individual in your pipeline. My second hypothesis is markerless systems, when you're looking at specific angles and standard movements, are going to be just as good as marker-based systems. So my first prediction, I think for stride lengths, they're going to have similar data. And for joint angles such as squats or lunges, where you just look at knee angles and you're just focused on that specific data set, they're going to have similar data. And if this is true, we could encourage more use of markerless systems because of how much easier it is to set up and use. So for an experimental setup, I want to get 20 healthy adults that are athletic and non-athletic, and I want to start off with one camera, one markerless and one marker-based camera, and slowly increase the number of cameras we use so we can get a threshold on accuracy with camera while we do the experiments. And this will help create that guidebook that I talked about for individuals to use to understand when to use which system. So to test hypothesis one prediction A about dynamic movements, I want the individuals to do sprints and jumps, and I want to test whether the marker-based system and the markerless system are equally accurate for those fast movements. And for the second part of hypothesis one, which is prediction B, where we look at the full skeletal model, I want the subjects to just walk around and do some squats, and I want to see how much of that skeletal model is captured accurately with both systems. For hypothesis two, prediction A, I want to assess stride length on a treadmill and frequency using both systems. And for hypothesis two, prediction B, I want to compare squat and joint angles, so that your knee angle as you squat for hypothesis two, prediction B. So in order to test the validity and how much the system has evolved since the last time I've seen it, I created my own markerless system using Python and OpenCV. And I essentially placed these anatomical virtual markers on myself using this library on VS Code, and this is kind of how it works. And I just looked at my elbow flexion and extension angle to see, with a very basic computer camera that is cheap and affordable, how accurate can you get for markerless motion capture. So after doing this, this is the coordinates of the elbow markers as they move up and down for 30 seconds, and I did 3 separate trials for this. And I converted these coordinates into elbow flexion and extension trials. And as you can see, the data from trial 1 to trial 3 for elbow flexion and extension are pretty similar. And this speaks volumes that I was able to create a pipeline using a Python library in my room to get this type of accuracy. So just imagine when you use high quality cameras, how much more accurate the system could be with anatomical markers. And this is with no calibration whatsoever. So the potential impact of this markerless system is it's much faster to set up, and it's much more accessible to a wide variety of audiences because you don't have to wear tight clothing. You don't have to wear reflecting less clothing. You can just wear whatever you want. You could be in a wheelchair, etc. And you can use it in any environment because all you need to do is set up those cameras and calibrate it. And this could expand motion capturing to remote and non-lab settings. And we could do much faster trials and much more trials in one day with this markerless system. And the conclusion is by gauging the effectivity of the system, we can minimize setup time and operation time for clinical trials. And this assessment, this guidebook that I want to create to show how good markerless system is for specific tasks will allow researchers to more accurately and more efficiently gather data, which would be enormous in the biomechanical role to know when to use which system and save a lot of time and effort for future researchers. Thank you so much for listening to my presentation and have a good day.